I'd like to discuss what we're doing in Spring as it relates to using NoSQL. My background, I have a long history committing into the Spring projects, starting in 2003 around messaging functionality with JMS. I later went on to lead and found the Spring.NET project, which is the Spring framework in the .NET programming environment. And for the past couple of years, I've been leading the Spring Data family of projects, and we'll get into what that family is more in a moment. What I'd like to cover today is pretty long. Hopefully we'll get through it all. A quick overview of what's going on in the data access landscape, then move into discussions about NoSQL support, basically helper classes specific to each NoSQL database that we offer in Spring Data, and then show you some of the shared programming models and data access mechanisms that can be used across the different NoSQL databases. So as I'm sure most people on this call are familiar with, what's going on in the data access landscape is quite different than it was 5 years ago or 7 years ago, where relational databases were predominant and the only option really on the table. They're still important and they're still predominant, but there is a class of new databases that's coming up that address problems that relational databases can't. These usually relate to the limitations that we're probably familiar with as it relates to scaling out a database and scaling up. And a lot of data that's coming in now and being collected is semi-structured textual data. It doesn't map very well onto a rigid schema. So not only is performance as it relates to inserts and operations a concern, the actual relational model itself for certain classes of use cases is not appropriate. So these new data access technologies have some different characteristics overall. Each one is sort of unique, but they generally have a limited transaction model and usually a relaxed consistency model. And it's common right now when developing new applications to have a different perspective around your data access layer, where it's becoming more commonplace to have a combination of a relational database and another NoSQL database together in a solution, each addressing the class of problems that they're best suited for. So it's sort of a best tool for the job scenario. So Spring has always historically provided very rich data access support. This goes back to the early days of Spring in the 2002-03 timeframe. Declarative transaction management was there. Portable data access exception hierarchy is quite important when you're creating a data access layer, so that your service layer can catch exceptions that are not technology specific, increasing the portability of your app. JDBC template was a helper class that was very popular in the early days of Spring and still is if you're going to be using SQL straight against the database. This is a very common use case to use JDBC template. There was also rich object relational mapping with Hibernate, and now moving on to JPA, of course, and other technologies such as JDO and IBATIS. And most recently in Spring 3.1, there was introduced declarative caching support as well. So the goal of Spring Data is to sort of refresh its data access support in light of the new data access landscape, and still keeping in mind the key benefits that Spring has always brought to the table. These are the concerns of modularity, productivity, portability, and testability. So I'm not a huge fan of mission statements, but I think it helps to have one. What we, in a nutshell, would like to do is provide a Spring developer a familiar and consistent programming model for a range of topics, namely big data, NoSQL, and also relational stores. and do this while retaining store-specific features and capabilities. And it's really worth emphasizing that last point. Spring is often noted for providing abstractions, and we'll have some discussion of commonality across different data stores. But I want you to go away with the impression that if you're using one particular NoSQL database and you like all the features of that database and you want to get access to all those features, Spring is making that easier. It's not making it a one-size-all situation and a lowest common denominator solution. So the term NoSQL is really a trend where developers are increasingly looking for non-relational databases to solve their problems in order to use the right tool for the right job. There's no sort of one model, and we'll get into some of the models in a moment. Query mechanisms, for example, in relational, of course, you have SQL. And NoSQL doesn't mean you can't query it. There are, in fact, a variety of query mechanisms depending on which database you're looking at. This could be as simple as key lookup, programming model, MapReduce, or query by example, as well as having query language itself, much like you would be accustomed to with SQL-like language. Big data is a terminology that comes up as well. It's in our mission statement. And here I'm just categorizing it as a data set whose size is beyond the typical database software size. This is a subjective and moving target. If you asked what was big data 10 years ago, you get a different answer than today because of the increase in capacity and CPU of machines. But if you look at today's hardware, you'd say this would range from the tens of terabytes to multiple petabytes. So the broad view of the Spring Data project can be mapped onto these categories here. We have new support for dealing with relational databases. These are in the Spring Data JPA and JDBC Extensions project, which we spoke about in the webinar a couple weeks ago. So if you want more information on that, you can go back to that webinar and have a look. We support a pretty wide range of NoSQL databases: Redis, HBase, Mongo, Neo4j, Lucene, and Gemfire as a distributed data grid. And we'll go over 4 of those throughout the course of this webinar. We also have a category of projects that are grouped under the name Access. How do you get at the data? There's a repository abstraction, which is essentially helping you write a data access layer for storing your POJOs. We integrate quite a lot with the QueryDSL project, which we'll also discuss later as a type-safe query language. And we provide a way for you to export repositories or your data layer over HTTP using JSON and RESTful semantics. So what's in red is the area that we'll be covering, diving into more of what Spring offers in NoSQL and access to those NoSQL databases. So a quick tour of a taxonomy that one can apply to the NoSQL space. Each NoSQL database is unique. They all offer different features, even within the same data model, but it is still a good guide to look at the space from this perspective. There are essentially 4 data models that you can see in the NoSQL space that have become predominant. The first is very familiar. It's a key value database, and this is a familiar hash table-like function, data structure. And NoSQL databases such as Redis, React, Voldemort are based on this data model at heart. These usually come from an Amazon Dynamo paper that was published a while ago in terms of how it would handle resiliency and replication to have a very high availability. The column family series of database, you can consider it an extension of the key value data model. It's where the values can also be key value pairs themselves. So if we had a representation of that, you'd have a key, and on the left side you see A, B, BB, and C. Those are keys, And on the right side, you have key-value pairs themselves. HBase and Cassandra are examples of this, and in terms of how they're implemented as a system, Google Big Table paper is often used as a source of inspiration for implementing these systems. Here I show what they call super columns, which are yet an even more nested grouping of key-value pairs, something that these column family databases support. Document databases, in essence, we're probably familiar with these in the guise of XML databases, which were on the scene for quite a while. But predominantly now, the format that people want to store data in is JSON. CouchDB and MongoDB are examples of document databases, although widely different from each other. And in this case, the document, if it's in JSON form, looks something like this. You see on the right here where you can have simple key-value pairs, but you can also have more rich data structures embedded, such as arrays. And you can have pointers to other documents as well. In this case, the ID serves as the identification field, the unique identification field for the document stored in a collection. Graph databases are also quite interesting. You know, think back to when you were in school and learning about graphs. They have nodes and edges, and they're directed. That you can have one node pointing to another node, and that pointing to represents a relationship or an edge. And each of those nodes and edges may have properties, simple key-value pairs essentially, tacked on to those nodes and edges. And as you can imagine, in the world of social media, a graph of your friends is a very natural representation to store data if you want to explore who knows who or get recommendation algorithms. So here I put on the screen now a better indication of how each node, for example, could have a property such as a name or an age, and so on. And relationships can be named and also have properties. So there are two major themes in Spring Data, as I was mentioning earlier, that we do offer very rich support for database-specific features, and they're accessed through a very familiar Spring template pattern. If you've used any of the template classes in Spring before, such as JDBC template, JMS template, REST template, they all have a sort of similar design pattern where there's a common low-level callback that gives you access to underlying resources. So, for example, in the case of JMS template, you might get access to the connection, and JMS template, maybe the session. And this carries over into the NoSQL data stores. There's a lower-level execute callback that gives you access to the lower-level infrastructure, plus a series of helper methods to help you with very common day-to-day tasks. And these take care of things such as resource management, meaning the opening and closing of connections or caching of those connections, as well as participation in transactions if the database supports transaction, and performing exception translation, again, into Spring's portable data access exception hierarchy. So we have that theme that runs through all the specific support for these NoSQL databases, and what we have developed are ones for Redis, HBase, Mongo, Neo4j, and Gemfire. On the flip side, if you just want to store a simple POJO, like a person class with some names, and do create, update, delete, we have a repository programming model, which is an interface, which is quite common when you're running a data access layer that has finders and has create and update, delete methods. And you would write an interface, and we would provide an implementation, and we can provide this implementation across different NoSQL data stores. Not all of them that we have listed, but a good range. There is also integration with QueryDSL, which is a type-safe DSL for querying. We'll see a bit of that later, as well as export these repositories over HTTP in a RESTful-like manner. So now I'll do a tour of 4 of these NoSQL database helper classes or template classes to give you a flavor for both the data stores and for how you can access them in Spring. So Redis can be thought of as a very advanced key value store because values can have complexity. They can be a simple string, as you would expect, but they can also be a list of strings. They can be sets. They can be sorted sets, or they can be hashes. So there's quite a lot of richness in the data structures that one can store inside of Redis. And the operations you can perform on each of these data types is unique to that data type. So if it's a list, you can append to the list or retrieve a slice of the list, which is something you wouldn't do on a simple key value store. It's very fast. There is good documentation on the sort of ON notation of how long operations take. Many of them are in constant time, and you can get up to 100,000 operations per second on basic hardware. When you're dealing with things such as sets, it's quite common. You might want to do differences and unions and intersections, and this actually can help you perform equivalent sort of selection criteria that you might be used to if you were using a SQL database. Another important characteristic of Redis is that it's single-threaded, despite being that fast, or actually probably because it is single-threaded. It's written in C, and this allows you to have atomic operations. So you can, for example, have a counter that's shared across your cluster, and Redis can maintain that counter consistently across all members of the cluster. There's persistence, and there's additional master-slave replication capabilities. If you want to know more about it, you can go to Redis.io, and there's quite a lot of documentation there. Redis comes with a command line interface. You can just fire it up after you start the server. And here I show a very basic example of setting the name of a key foo to 1 and then getting it back. Here I create a set, and you can add members into the set. In this case, we're adding members A and B, letters. You can remove, and then you can ask to get the members in the set. So very, very basic operations, but they're quite powerful in practice. And so what Spring Data Redis allows you to do is it, first of all, provides a de facto API for Redis on top of multiple drivers. There are about 4 drivers out there. We support all 4, and they're all sort of gratuitously different in their APIs. And so we insulate your client code from the differences in the underlying driver library. The fact of the matter is that the client libraries for Redis are maintained by community members, and over the past 2 or 3 years, you see an ebb and flow over which ones are maintained more. And so this helps shield you from those changes. The Redis template is the heart of the support class we offer for Redis. It has resource management, the translation into Spring's data access exception hierarchy, and more importantly, Redis fundamentally is dealing with byte arrays that you send over the connection. When you look at the underlying driver libraries, they are typically at the byte array level, and we provide serializers so that you can operate at a slightly higher level. For example, we support serialization of objects using a convert and set method, to Java JDK serialization. Strings is actually a very common case. We have a dedicated string Redis template class for that. JSON and XML serialization via Spring's Oxen package. And you can have your own custom key or value serializers. Another interesting feature, if you're familiar with the JDK collection classes and atomic counters, those can be used, those interfaces sit, list, and map, and backed by Redis, so they'll be persistent, and I'll show you an example of that. So that's a nice case of taking a very familiar API, adding a different implementation that provides persistence and this atomic functionality. So here's an example of a Redis template. Here I've parameterized it by a string in person. I haven't shown yet how you would configure that Redis template to have it auto-wired, but just for the introductory example, suppose we have a person. I picked one of my favorite comedians, George Carlin, and you create it, and now on Redis template, there's a series of methods where you can get a family of operations for a particular data type of the 5 data types. So you have ops for list, ops for set, and so on. And then you can say, I would like to push, in this case, onto the left side of the list, this person. Another interesting functionality in Redis, Redis is it has a lightweight publish, subscribe sort of middleware system. So you can also use that much like you used a JMS template or a Rabbit template, and say I'd like to convert and send to the topic dialog the string hello world, or I'd like to convert and send to the topic webinar :joined this person. So that's the sending side. On the receiving side, if you're coding against the low-level drivers, you have a bit of work ahead of you to do connection management properly. So we've taken care of that asynchronous receiving infrastructure by providing a message listener container in the same spirit as Spring's message listener container implementations for JMS or for Rabbit. So this allows you to have message-driven POJOs for Redis. So for example, here's a message-driven POJO class. I have a receive method. It takes a string, just doing a simple printout to the console. And in the configuration, I would bootstrap a listener container pointing to Redis's connection factory. I would declare that I would like to invoke the method receive on the listener MDB method, and the topic would be chat room, and there are wildcards that you can use in the topic as well. So channel star allows you to do wildcard subscriptions. So here's a small example of using the JDK collection classes as well as, just the JDK collection classes. I didn't show the atomic long, sorry. No, I didn't. Oops, sorry. There we go. So you create a Redis set, and you give it a name. That's the name that would appear in Redis. And you give it the connection to Redis, the Redis connection object, so that it can be persisted. And then you can use the sets as you would normally use them in the JDK APIs. And you can do things like intersection, union, and join, and so on. I think that's quite neat. If you're familiar with Spring's cache abstraction, it was introduced in Spring 3.1. There's an annotation at cacheable where you provide the name of cache and give it a key and the condition under which you'd cache the method invocation using spell expressions. And then it's very simple to plug that in. There's a provided class called Redis Cache Manager that gets picked up when you specify the cache annotation-driven XML. Okay, moving on to the column-oriented database, HBase is one of those, and it has columns that are pointed to in a row, and those are actually key-value pairs themselves, and they can be further grouped into what are called column families. And what's important is that these column families are optimized for storing on disk in terms of I/O performance. So we'll see an example in a minute where we have 2 column families, and the general idea is that data that's in one column family lives closely together on disk. So if you're accessing a group of data more frequently than another, you don't have to traverse all of the data on disk to get just, for example, 28%, and that would result in a faster I/O performance. So data is stored in HDFS, and it's modeled after, which is from the Hadoop project. So it's a Hadoop family ecosystem project, and it's modeled very much after the Google Bigtable paper that described a lot of the algorithms used to make this technology work. Google itself had a Google file system, which was in turn used by the Apache project to make HDFS. So you do need to define a schema, a very rough schema for the column families up front. So namely, I like 2 column families. But once you have those column families, the data that's inside of those can change, and there's some flexibility you have in the schema. So as with Redis, there's a shell that you can use in HBase to explore in the beginning to get used to the data model. You just start that up by saying HBase shell. And here I show an example of creating a users table that has two column families, one column family called CF info and another column family called CF status. And so we're separating commonly used data such as username, email, and password from less frequently accessed data such as do they have a valid email. I put some data in here into each column of the row. So here in the first case, I'm putting in row 1 the user information for the column family CF info. Again, same row, column family, putting in the email address, similar for the password, and so on. So then you can use scan, which is their sort of select star, and see that in row 1 you have all this information. And implicitly, every row and column value gets a timestamp for that particular cell. If you're just using the native API in HBase, you would create a new Hadoop configuration object. You create an HTable class, an instance of that, and there are a series of operations such as put, in which you would then put stuff into the table. I think this is showing the same thing here. Yes, it is. So the API has a number of shortcomings that make it very tedious to use in practice. The number one issue is that the HTable class itself is not thread safe. So I don't show the resource management required to properly use the table here, but suffice to say, it's a series of try-catch blocks that is not particularly fun and quite boilerplate. In addition, it throws HBase specific exceptions, so that means your service layer calling into this data access layer would need to be aware of that. So those are the scope of things that we've tried to address first in HBase. There's more we can do, but that's a start. So in the Spring for Apache Hadoop project is where you find our HBase template class. It takes care of the resource management for thread safety of the underlying API, as well as the translation into Spring's DAO hierarchy. And we also provided an object mapping framework inspired by what you find in JDBC template. So it should be familiar to you in that regard. These are callbacks that define the mapping from the HBase result set when you make a scan query into POJOs. These are row mappers, result extractors, and then there's the lowest level table callback where you can do more low-level operations. So here's an example of the configuration you would put in a Spring XML file. The configuration class here is related to Hadoop. The first one, where to point to HDFS. The HBase configuration, in turn, piggybacks on top of that. And then you instantiate an HBase template and pass it the configuration of HBase. So here's some examples using the lower level execute method on the template class, which gives you access to the underlying table, so you don't have to worry about the resource management or exception translation. And here you see we're doing the equivalent operations of putting in user, email, and password. We still haven't made any helper classes on top of many higher level helper classes as it relates to not dealing with the byte array aspect of the underlying driver, but we'll get to that eventually. On the bottom here, you see an example of using the find method. There are several overloaded versions of that. You can pass in a scan object to customize quite a lot about what you're querying for. But the primary case here is to show the use of the row mapper that will map the result set from that find call in HBase template and into a POJO, in this case a list of users. So moving on to MongoDB. MongoDB is a document database. It provides documents that are stored in JSON. syntax. Under the covers is actually a binary representation on disk, but for all intents and purposes, just think of it as normal JSON. And it's schemaless, meaning that just like you have a JSON data structure, there's nothing ahead of time defined, unlike, for example, in the case of HBase, where at least you had defined column families. Documents are organized into collections. That's the grouping, and you usually deal with collections of documents when you're addressing the database. Its model for transactions is essentially you can atomically update multiple fields inside of a single JSON document, but not multiple. You can update all of the document, and what's actually quite common is to update, for example, just part of the document, like increment a counter is a good example. You might have how many times a person logged in, and you might have a logged in field, and then you can just tell Mongo to update that one field, and that would be done atomically. There is a very rich query language for dynamic queries. It's not quite SQL, but it's still quite good. And in the early days of NoSQL, when there were not quite a lot of expressive query languages, Mongo certainly was there with something that was easy to wrap your head around compared to, say, writing a MapReduce operation in JavaScript. There's indexing. There's a nice grid file system, they call it, for file storage. Another cool feature is geospatial features. A lot of people pick the database for that particular use case, so you can store locations and then ask questions like, am I near this location? And as with most NoSQL databases, you can expect high performance and scalability. It does this through an auto-sharding mechanism as well as replication. So MongoDB also has an interactive shell. Here we show a very simple example where we have a record where we create a name key value pair. This is Chris Richardson's favorite restaurant in, I think, Oakland, California. And I save the restaurant and then ask for it back, and you can see it's been assigned automatically an object ID, that long 4E sort of hexy-like thing. And then you can execute on this collection called restaurants, find your method saying, I would like to find, sort of in a query by example style, the restaurants with the name Ajanta. Now I'm going to set, for example, a type to be Indian. This is all in the CLI. Save it, do a partial update, add some things into the new field called menu items, so that's a push operator. The set operator is what overrides the short name we gave before. Then now when I do the find, you see the document has more fields in it. It has the updated name of the restaurant, the type of the restaurant, and then a menu item structure, which in this case is a nested array. And then I can remove it. So that's a sort of insight into what's going on with Mongo. There's quite a lot of support that we have in Mongo template. One of the key features is mapping an application POJO onto what Mongo calls a DB object. That's their representation of JSON in the Java client API. The mapping is annotation-based, using some of the annotations we show here, at document, at ID, at field, dbref. dbref is a way you can refer to other documents, essentially a pointer from one document to another. There are update, query, and criteria fluent APIs that make using those operations much more terse and more natural versus using strings with $set operations and so on. You can use methods for that. As you'd expect, there's a translation into the Spring DAO exception hierarchy. And you can get at, as I mentioned before, very specific functionality to Mongo. It has a MapReduce framework. It has geospatial functionality. You can get access to the grid, file system support, all of this through this helper class. Actually, GridFS is a separate helper class for the grid file system. The other features, which we'll get into a little bit later, are around the repository support, QueryDSL support, And on the bottom here is a feature people often ask for, and we implemented, but hasn't really gotten a lot of use in practice, it seems, what we call cross-store persistence, where you can map part of your object into a relational database through JPA and other fields into Mongo. It sounds quite cool, and it is quite cool. I would love to see more people using it, a little bit more feedback. So here's the Mongo operations or Mongo template class. Mongo operations is the interface. We picked the same style as you might be familiar with JDBC template. For example, there's an operations interface, so if you want to mock or stub the interface in your code for some sort of integration test, that makes it possible to do that quite naturally. Here you see the low-level execute methods that are on templates to get at the low-level data structures that the client library offers, namely the collection or the database itself. But it's more common to use higher-level access methods. Here you see a find method that takes a query class. This is our Fluent Query API. Similarly, you can just save an object, passing in a collection name. You can update a object as well by specifying a query and what fields you would like to update in Fluent DSL style syntax. Similarly, there are specific methods around MapReduce, as well as doing searches for objects that are near a certain location. So here's a little code snip of some very basic usage to get you a feel for things. You instantiate a new Mongo template by passing in the name of a collection. In this case, we called it database, and the underlying Mongo connection client library from the driver. That's just called Mongo. Once you have one of these Mongo templates, or here we're just using the interface, you can very easily say insert a new person, which you can imagine is just a plain Pojo. Nothing specific to Mongo in that has a name and an age field. If I'd like to now do a find on that collection, I can then use this query helper class, and there's actually a little syntactic sugar not shown here where you can use static imports to get rid of that new, and then you can say query where that's coming in from a static import, name is Joe, right? So reads quite nicely. And then you can do collection maintenance, such as drop a collection, create a collection. On the bottom here, you see a point class as part of the Spring Data Mongo project that specifies a point. We also have other shapes. And then you can do a query near a given location specifying, a distance. And there are a bunch of different options of how you specify that distance. So once you have that query, you can say, I'd like to find restaurants that are near a certain location. So it's quite common use case for Mongo is to take advantage of those rich geolocation features. Here's an example showing the MapReduce framework in Mongo template. There's a sample document up there. It's very simple, IDs, and then there's one field X that has an array of letters. I won't walk through the map function, but basically is counting the occurrence of each letter in the array. The reduce function is summing up the occurrence of each letter across all of the documents. So whatever was emitted by the map is then collected or reduced in the reduce function. And then Mongo template lets you run this MapReduce, and you can reference these JavaScript files using Spring's resource notation. So class path is a common one. And then map the results. In this case, we have a very basic value object that represents the results. So that's one way you can get at the low-level MapReduce operations. For the configuration, there's a couple ways you can bootstrap yourself. We've been pretty consistent across all the Spring Data projects to offer both XML support and Java config support. Here you see the XML on the top, where you create a MongoDB factory and then pass that into Mongo template. What's important there to keep in mind if using Mongo is that the write concern, the default isn't safe, although now the newest client library from Mongo is changing those defaults. But here we show explicitly setting it to safe, which means getting an acknowledgement back from the driver when the server has stored it. On the bottom side, we provide an abstract Mongo configuration class that creates the Mongo template. All you have to do is provide a database name as well as the core driver Mongo class, which usually points to a specific location on the network where the server is sitting. So for the last database we'll cover very briefly is Neo4j. It's a graph database. As you'd expect, it's focused on connected data, the connections that are between data. It's obviously extremely rich in this regard. If you think of a social graph, as I was saying, or even on GitHub, it's quite cool to see all the relations between projects. You can do some really cool things with Neo and that type of use case. It's a schema-free database as well. It specifically is a property graph where the nodes and edges can contain properties. Unlike all the other databases I spoke about so far, it actually does offer full ACID semantics for transactions. So that's quite nice. There's indexing capability on particular properties in the graph, quite scalable. There is a REST API to talk to a server, or if you're on the JVM, you can embed it inside your own application, which is also pretty cool. There's a declarative query language that came on the scene a couple years ago called Cypher. As you can tell, maybe not tell, but Cypher is one of the characters in the Matrix movie. So they, I think, win the award for coolest examples because they picked all the characters from the Matrix. So Spring Data Neo4j, it provides a mapping functionality. I'll show an example of the native Neo4j API, but instead of dealing with nodes and edges, you deal with POJOs that in turn get their state backed onto nodes and edges in the graph. There's support for beam validation, all the query and traversal support you get from Neo. It also has this cross-star persistence support where part of an object can live and be mapped through JPA into a relational database and another part managed by Neo. Exception translation, the cloud transaction management, so there's a Neo4j transaction manager. And we'll see later the repository and QueryDSL support. There's also an XML namespace to make bootstrapping a little bit easier in the XML. So here's a classic domain class, as it would be called in Neo4j. I'm creating a tag, very simple data structure. And what you'll notice here is that you're dealing directly with the Neo4j graph objects. You're dealing with a node. And if you want to set a name on this tag object, you have to access the underlying node and get or set the property. And as you can imagine, as you do more and more and more of this, it results in a fair amount of boilerplate code. So instead, there's a programming model offered by Spring Data Neo4j, and I should mention that we worked incredibly closely with the Neo4j team. In fact, I'd say they've done 95% of all the real hard work, and we provided some guidance. So it's really spot on with their vision of how they would like to see POJO mapping done into Neo4j. And this is through a node entity annotation, for example, for nodes that represents a node in the graph, and you can give it an ID, just like you would in any other database for uniqueness. And then you can say, I would like to map on the private field string. In this case, I'm also asking it to be indexed. So that's quite interesting. There are two modes in which this mapping occurs, one AspectJ-based and one that's more proxy-based. But I won't get into all those details. But suffice it to say, it's a very simplified programming model from what you would have gotten out of the box with Neo4j. Here's just another example that shows how it might be used where you're having a customer object and the customer has a relationship to a set of addresses. Here we're relying on the relationship called address to traverse across one node to a set of other nodes that contain address information. So as you've seen before in the other template classes, Neo4j template provides resource management, integrates with Spring's to cloud transaction management, exception translation, provides lots of convenience methods to make common operations in Neo, sort of one-liners, and it can work with the REST server as well as the embedded server. And there's query languages that Neo4j supports, Cypher and Gremlin, are two of them. Those are commonly used query mechanisms. And there's some syntax sugar on how to handle the results with a Fluent API. So I didn't show here a query. If you check back for the deck when it gets posted, I'll probably put that up. But here's just a basic example of how you'd save with Neo4j template. I'm just saving a few customers and products, and then saving an order that has those relationships, items, with a particular order that's associated to a customer. On the bottom is the simple XML boilerplate code you'd use to bootstrap talking to the Neo4j server over HTTP. And when you use the Neo4j namespace and specify what graph database you're talking to, it implicitly creates a Neo4j template in the application context that you can then reference by using an auto-wired annotation, for example. So with the last few minutes here, I'd like to very quickly go through what are the shared ideas that we have available across the different NoSQL databases. Again, we try as much as possible to give you the typical escape hatch. So if you want to go down to more specific functionality, you're not locked into an abstraction that doesn't work for your particular database. So repositories are the thing I'll spend the most time on, and I'll just quickly touch on QueryDSL and the REST exporters. So the repositories are essentially your data access layer. It's what mediates between your data source and your business entities responsible for the mapping and execution of queries into POJOs. And so the theme of the Spring Data Repository abstraction is to remove the busy work you often see in building a repository or building a data access layer. So there's a simple recipe. You basically use annotations to map your POJO as you would normally. You can extend a Spring repository marker interface or use an annotation on an interface. Add some finder methods according to a specific naming convention, and then Spring will scan the class path to look for these repository interfaces and create the implementations for you. So you're really just coding interface code and not actually any Java classes. And now, once those 4 steps are done, you can reference those interfaces as you would any other managed bean inside the application context. And what's nice here is we provide consistent support of this programming model across JPA, Mongo, Neo4j, and Gemfire. And if you need to drop down to specific native database functionality, you can, but there is a bit of commonality one can achieve across them. So the top-level features for the Spring Data Repository are basic CRUD features, create, update, and delete methods, and then support for finder methods that follow a specific naming convention. So I think we can all imagine what find by name does, right? It looks for a particular object and makes sure that the name is equal to a certain value you specify. Pagination and sorting is sort of a dark horse when people are writing data access layers. We provide support out of the box for paging and sorting, as well as some helper classes to help you integrate that functionality into a Spring MVC web application. If your CDI is your flavor of for dependency injection, then that's also supported. So here's a Spring Data Repository interface. You can see this one's just a marker on the top. The CRUD repository is what brings in save, find, delete methods, and you can extend that. You can also do a form of duck typing where you just pick some of these methods and put it on your own interface. That works as well, but isn't the easiest thing to get started with just from an introductory point of view. So the common case is to extend, you would extend that CRUD repository case. Paging and sorting is a sub-interface of CRUD repository that adds functionality for finding based on sort criteria or based on page criteria. And those return pages, objects. So So here we see an example, picture a person, has a name, and an email address, and an age. And we extend CRUD repository, so that means we get all the functionality for create, update, and basic finds. But now we add methods, much like you would do in Grails or in Ruby on Rails, that imply a query. So find by email address, find by last name like, find by first name like. All of these will be implemented by the Spring Data repository infrastructure, so you don't actually have to implement that. So here I show an example of the translation that goes on with find by email, for example. I mean, for the custom finders, I show it for the equivalent JPQL, but I think you can imagine how this would translate into other query languages that you might be familiar with, such as Mongo or Neo4j's query language. So we support all these keywords that you can use inside the method name, find by last name and first name, greater than, find by age greater than, and so on down the line. So this is the little trick we use in order to provide some portability across the different data stores for finders. So just taking it step by step in, say, the case of Mongo, here we create an entity, a person, and we use the Mongo mapping annotations, document, ID, field, dbref, and so on. Now you define your own repository interface. Here, for example, I'm just extending the marker interface and adding a few finders. So in this case, it's doing only finding and no create, update, delete functionality at all. If I wanted to have, for example, just create, I could put in this person repository interface a method signature that mimics the individual method on CRUD repository, and the infrastructure would recognize that in a sort of form of duck typing, you might say. If you don't want to extend a marker interface at all, you can use an annotation instead to provide the necessary information about the domain class and the type of the key. So here you see we're also allowing you to use native functionality that's specific to Mongo. So find by email address, find by last name like, by first name like. These are things that you can imagine are quite portable across different implementations. But we still let you access functionality that's specific, let's say in this case to Mongo, by doing geospatial queries, and we would provide the implementation for those. So this is find by location near, for example. So how you bootstrap this, you can use Java config, in which case it's actually quite simple. You have an enable Mongo repositories annotation, or you can use XML where you specify the base package where those interfaces or classes with that repository definition annotation live. And once you do that, you can then use them, inject them, for example, into any client as normal, and off you go. Here I show again how you can drill down to get at more specific database functionality unique to each data store. The query annotation here lets you specify the query not by a derivation from the method name, but explicitly providing the Mongo query syntax, which is a JSON-like syntax. And so what I show here is exactly the same repository interface, but we're using this one against JPA. And here I show how you can use JPA-QL, for example, to do the same sort of functionality where one is overriding the type of query that's figured out from parsing the method name and executing that specific JPQL, or you can also reference a named query there. And you can also put on these methods various other annotations to specify the lock mode and specific transactional metadata, query hints, and so on that's very unique and specific to JPA. Quite nicely, there's tooling support for all this. So if you have a customer repository in your Eclipse or IntelliJ project, and you're deciding to create a new repository interface, and you make a typo, namely that I'm trying to query against a product, and the product has a description, and in this method name I made a typo and forgot the I inside of description, you'll get a little X that says there's no such type description, no I, on the domain type. So similarly here I'm showing this is a JPA case, but it would apply for all the other technologies we support. Is an order is being mapped. And now also I can get drop-down completion. I have to say find by, do control space. It'll give me, billing address, customer, shipping address as possible completions, because those are the properties that are mapped on the domain object. And it continues if you do find by billing address and so, you can construct those methods. So I know we're running out of time, but I just want to quickly go through maybe 2 or 3 more slides about QueryDSL. QueryDSL is a separate project run by people at a company called Mycema. You can access that project at querydsl.com. And what this project is trying to address is the basic fact that using strings to represent queries in code is very error-prone. I'm sure everyone here on the call has made a typo and only discovered the typo in your query syntax when you actually ran an integration test or ran the application. So what QueryDSL does is it uses a code generation technique to provide a query language that's type safe. It's a very fluent and compact syntax, and that means you can get auto-completion inside your IDEs. And most importantly, what's I think very interesting about it is that it provides a query language with a consistent API, but is tailored to each individual backend. So there's support for JPA, JDO, SQL, MongoDB, Neo4j. And what I mean by tailoring is that, for example, aggregate operations in MongoDB usually require a sort of separate step to group by. So group by wouldn't be one of the operations you'd see in the Mongo dialect of QueryDSL, but you would see it, of course, in the JPA or SQL case. And it's Apache licensed. So this functionality is integrated into the Spring Data repository support by adding this interface into your particular repository. Predicate is the expression that is part of the type-safe QueryDSL. It's the class that comes from the project. And on the bottom here, you can see an example of how this would work querying for a product. You would say, I'd like to find one product, and you use this product class generated from the tooling, and you say product.name equals iPad. Or you can say product.description contains tablet, and you say find all of the tablets. And you could, do dot and, product dot, is in inventory equals true, and so on, and construct very nice fluent queries. I suggest you check it out. Just 2 words on Spring Data REST. It's another way to access information that is inside these CRUD repositories through RESTful semantics, so we can map put and post onto save, gets onto finder methods, deletes onto delete methods. And we support JSON as the first-class data format. It's implemented as a Spring MVC application. Right now we support just JPA-backed repositories, but we're in the process of supporting it for all the other cases such as Mongo, Gemfire, Neo4j. It's a very discoverable type of export, meaning if you get on the root path, you discover what other resources are available, and resources are related by links. This builds up off of a project called Spring Hate AOS that is the basis for creating these linked representations. A very quick example that comes from the demo we have. Imagine we had a person object, person repository, and we just go to the root of the web application and say, what's there? You can see that we have a person resource. If I query into that person resource, you see I can do operations such as search. If I then search, you can see which search methods effectively are returned. There's ways to customize that, which we won't get into. And then you can actually execute one of those searches and get a link back to the person that was a result of that search. And if you get a representation now of that person, you can now see its property is a name, and it also has lots of other links to its other relations, such as profiles and addresses and so on. So that's as much as I want to go through. There's quite a lot. As you can see, I didn't cover Lucene or Gemfire. The main landing page for more information is Spring Data. QueryDSL project, QueryDSL.com. There are quite a lot of examples out there to help you get started. Many are listed on the individual project pages. There is a book that we've written where we wrote quite a number of examples. Spring Data Book is a GitHub repository for that. And there's sort of almost Maven archetype-like style projects inside this Spring Data Kickstart project. This is the book on the left is one that the Spring Data team wrote. The book on the right is from another independent person, and you can now, for example, get a free chapter from a promotion we're running related to JPA using the repository approach, and a general link to get at the book is shown down here, and it covers the entire range of functionality we just covered. So with that, I'd like to go to the Q&A that's been building up over the session and answer some of the questions here. Let me scroll through. When is it expected to see Cassandra support from Spring? That's probably our number one question. The answer is we don't know. We don't have anything on our roadmap yet. We would like to get to it. If you're interested to help out, please get in touch with us. Second question here, is H-based template part of Spring for Apache Hadoop, not Spring Data? Spring for Apache Hadoop is part of the overall Spring Data umbrella, but I kind of get the idea you're saying, why isn't there a Spring Data H-base? Right now, we thought this was the best way to approach it. H-based functionality and Hadoop are very, very closely linked, and we wanted to start in that manner. If there's a need to separate the projects at some point, we'll do that. Please explain, is user class a POJO nature or some lib class? Probably referring to something with the mapping. So in that case, yes, it's a POJO in the sense that there are mapping annotations, but no other specific infrastructure imports into the class. Does Mongo template use some Oxum to map objects from JSON and vice versa? No, Oxum is XML, and the underlying format in Mongo is JSON-like. Actually, it's a data format they call BSON, binary JSON, effectively. I think bson.org has some information on it. This is represented in the Java driver as DB objects, so we map POJOs into DB objects or nested DB objects. Think of DB object effectively as a map. Can you somehow hide methods from CRUD repository? You can't hide methods from the interface, but if you only want to expose, for example, I don't know, just a create method, for example, you could create your own interface and just stick in it that one create method that has the exact same signature from CRUD repository, and then you'd have an interface that only has a subset of the CRUD functionality, in this case just a create. I already addressed the question on Cassandra. Can we customize Mongo write concern on a per update insert instruction level? It's a good question. I believe I have to double check. I have to double check if there's, I think the answer is yes. If I bring up the Java docs, I think there is an overloaded method on update which takes the write concern, but I would have to double check. So how does Spring convert POJOs to Mongo objects? There is a pretty rich converter class, essentially, that also ties into Spring's conversion service infrastructure as an extension point. So there's basically a class we've written that handles that. Cassandra has a native support for JDBC. Can I use a JDBC class like JDBC template? Yeah, if any of these NoSQL stores offer a JDBC interface, then you can use all of the functionality that comes with JDBC. So, for example, in the Hadoop community, Hive is a way to access and analyze data in Hadoop. It offers a JDBC interface, and you can use that driver, JDBC driver for Hive with JDBC template. So the last question here, is there a way to access native Mongo API when using Mongo template? Yes, there is. There's always in the template classes the theme of having the lowest level of the native driver available to you. These are shown on the screen here. They're always named execute. And then inside that execute method, you get access to, in this case, the database itself, and that DB callback gives you the DB object, which is the native driver DB object of Mongo. And in the other case, it gives you the collection that maps either to that class or that string collection name you give. So that's the native Mongo collection. And what's going on in the execute method is it typically is wrapping up any exception handling, any participation in declarative transactions, and mapping into Spring's data access exception hierarchy. I think there was another example of execute floating around here. I think it was in the HBase case. Just show that as well. Oops, that's not quite what I wanted. It didn't go where I expected. Here we go, HBase template. There we go. So you see HBase template execute, and the low-level resource here is the table. So that is literally the table class, htable class. But the advantage of it being inside of the execute callback is you don't have to worry about the resource management, how to close that correctly, and so on. Okay, well, thank you, everyone. I believe I answered all the questions. I know it went 10 minutes over here. If you need to get in touch, please contact us on the forums or raise an issue on Jira. Thank you very much, everyone. Cheers.